Okay, so I want to direct your attention back over to the board. Not much has changed. You have your assignment that is due today, the vocabulary, and otherwise all of this stuff was either due Sunday or further in the week. I did update the reading because some of the content that you're going to be doing your prepare to learn over is going to be over naming compounds. So you want to be looking at that. I thought it might be helpful for the quiz to know what the quiz is going to be over. So underneath there, I have put that it will cover chapter 1. It will focus on the things we did in class. So don't expect to see things like any historical information that's in chapter 1. I won't go over that. And then in chapter 2, the stuff we did about the development of the atomic model and Dalton, that's going to be on there. And then the ions and isotopes, we'll be talking about how to find the charges of the different ions, what's the difference between an anion and a cation, but also you have that sheet that has the list of ion names. Remember that it is the bold ones that are on the, what is this, left-hand side that you need to know, and just the ions. So you don't need to know the bottom 2 ones that don't have a charge. Though you probably know water. So any questions about that? Yes.
How do you usually break up those quizzes, multiple choice?
Typically, most quizzes will have a handful of multiple choice. I try to put short answer at the beginning and problems at the end, things that you might have to do more calculation. We won't have that on this one. So it might end with multiple choice, or I might have something where you have to explain something at the end. So if I decide to put something in like, how did Rutherford know that the nucleus was positively charged? That might be at the end. So that's kind of how it works. Do look at, remember that I have on Canvas a page that is old quizzes and tests, and you can kind of see how I've asked the questions in the past, how they're organized, and just going through and taking that as if that were the quiz or the test, it can be a really helpful preparation, letting you know, oh, do I know this or do I not know this? For the ions, I had a couple of people ask me about this. I will either give you the formula and you have to give me the name, or I will give you the name and you have to give me the formula, but the charge matters. So if you say it's +2 when it's -1, then that's going to count off on you. So it's usually worth 2 points, one for getting the formula right, one for getting the charge right. So just kind of keep that in mind for those. For the list that you have here, almost all of them end in 8. Later on, you're going to have to learn the difference between the 8s and the ites. But for right now, 8 is kind of the big thing to be thinking about. And then there are a few that end in I. And, so that's kind of the difference there. Other questions? Okay. On your desktop, there should be whiteboards and pens. And so I'm just wanting to quiz you very briefly. You are going to put either a P or a C, P for physical, C for chemical. Okay. So I am going to pull up some pictures. Now, when we have a, first let me pull this up. If I am looking at the circles, remember those represent individual atoms. Different colors tell me that I have different elements. If you are colorblind, please let me know so I can make sure that I have a different way to distinguish it when you're being quizzed on it. And then if you have a change, it might change where these things are. But if it is the same molecule, so like this is a blue and a red together in C, and this is a blue and a red together in D, those are the same molecules, then we would say that's a physical change. Now, something I want to remind you of when we were talking about how we represent these, that for these, we've got the blue is kind of a complete circle, but then the red is sort of mushed on. If they're both complete circles, that just means they're sitting next to each other. So these are sitting next to each other. They're not mushed together. These are bonded. So this is how you can tell this isn't just one big molecule, is you can distinguish complete circles from things that are actually mushed together. Okay, so let's take a look at this, and you can feel free to check with your table mates, because I don't have a whiteboard for everybody, so discuss with the people at your table. Then tell me, do you think this is a physical change? Put the letter P, meaning there are no new chemicals, they're all the same. Or is it a chemical change, a C? You see different chemicals on the right than there were on the left. All right, so once you have decided, hold up your whiteboard so I can see it. All right, a plethora of C's. Yes, this is a chemical change. Now this one's a little bit tricky because we have a couple of the pairs of blues that remain. So these are just leftover or excess chemicals. But for the most part, we had reactions of all the red chemicals. Okay, next one. Here we have this dividing line means I put the top thing in one container and the bottom thing in another container. I've separated this. So separating those molecules, chemical or physical. Go ahead and hold up the whiteboard as soon as you have submitted your answer. Okay. Okay. All right. Yes, these are physical changes. So separating things, like if I boil water off and leave salt behind, that's just separating them. If I put something through a sifter to separate them, just a physical change. Okay, next one. Yeah. Yes. 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 Yeah. All chemical changes. Yeah, this is the first time we've seen triplets of molecules. So yes, that is a chemical change. Last one. Yes, 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 yes. This is physical. So we've just clumped these together. Now this is a process of going from a gas. Remember, we got these streaks here showing us it's a gas, to them gathered together in one of our condensed phases. A condensed phase might be a liquid or a solid, but because this is well organized, I would say this is probably a solid. What's the name of the process? Does anybody know, going from a gas to a solid? Deposition. What's the reverse, going from the solid to the gas? Sublimation. Okay, so we'll get to that at some other time. All right. Some things I want to point out are that if you have a phase change, like that one, or like boiling, you are not tearing apart those molecules or putting them together. Those are going to be your physical changes. So sometimes people think that boiling water produces oxygen and hydrogen. It does not. It just produces water molecules that are in the air. So those are physical changes. Okay. Next thing I want to talk about is the periodic table. So did everybody get one of these papers? Okay. So I like to tell people this is what I want you to memorize, because you're really always going to have the periodic tables. I'm not going to cover them up for quizzes or tests. So you don't need to memorize what's in the boxes. But I'm going to tell you some things that you should know so you can use the periodic table. So we number the columns. We call those columns groups. So each group is a column. Sometimes you will hear the term family, but more often group. So when we say family, we're usually using a particular name for it. And what I'm most interested in today is the outside groups or columns and what their charges are, because we're going to be talking ions and isotopes. We don't need this anymore. Okay. So common charges. Group 1, that very first column, which is in red on these periodic tables, those are always +1, which is convenient. Group 1 +1, easy to remember. Group 2 is +2. Now their names are very similar. Group 1 is the alkali metals, and group 2 is the alkaline earth metals. Okay, and those are what we call the family names. When we talk about families, we usually mean by those names. Those are mostly important to know because sometimes I'll say, if we look at the alkaline metals, I want you to know where to look on the periodic table. Okay, notice they are both metals. Now you have a big old block in the middle, which here is blue. That big old block is the transition metals. So notice we've gotten more than halfway across the periodic table and everything so far has been a match. The two groups at the bottom, which we won't deal too much with, these are also metals. Sometimes they are called the rare earth metals. You'll see on this periodic table, they're the lanthanoids and actinoids. You may have had a chemistry teacher call them the lanthanides and actinides. In chemistry, we like to use the ending "ide" to mean something that is negatively charged, but metals don't form negative charges, so that's why more modern periodic tables will say lanthanoid. I'm not too concerned about those, but they are metals. Okay, so all of this is metals. And then you'll notice there's kind of a diagonal line of brown here, or on this periodic table, there's sort of a zigzag line. You don't need to know this, but that is called the Zintel border. Everything that sits on that border, all the brown ones there, those are called metalloids or semi-metals, all right? We're not going to worry too much about those because mostly we're going to try and differentiate between metals and non-metals. And of course, semi-metals kind of behave like both metals and non-metals. So they're the kind of fuzzy area that we don't care too much about. But you should know that this is a dividing line, okay? There are also two elements that sit underneath it. So GE and SB, those also happen to be metalloids. All right, we'll talk to some later a time about what specifically makes them metalloids. All of this stuff up here in green and blue, these are all non-metals. Metals tend to form positive charges. Non-metals tend to form negative charges. That's going to be really important in the next section when we talk about ionic compounds, because ionic compounds come from combining positives and negatives. So we need to know which things are going to be positive and which things are going to be negative. Okay. I should put this over. All right, so we have our first two columns are +1 and +2. They're easy to remember. Then once we hit the transition metals here, transition metals can have multiple charges. Almost every transition metal can have a +2 charge, and then they all can have something other than +2. So the next column does like to form +3, but they can be +2. Some of them will form +4 or 5, up to 7, even 8, okay? So we can't say this is the common charge of iron because iron actually can go between +2 and +3, and sometimes it's +4. So we have to do special rules for those. When we name compounds, since we know group 1 is always going to be +1, we're not going to tell you the charge in the name. We're just going to say sodium. When we name something in group 2, like magnesium, we're just going to say magnesium. But if we were to do iron +3, the name is going to include that 3. It's going to say iron 3, so it will tell you the charge. So that's why I'm pointing this out, is that these two columns will never have the number in the name. These always will. Okay, next, we're gonna go to the other side of the periodic table. So the far column, group 18, is our noble gases. Now, sometimes they're called the rare gases, but they're actually not really rare. The third most common element in the atmosphere, or third most common gas in the atmosphere, is argon. So nitrogen was most abundant, about almost 80%, oxygen, and then argon. Way more than even carbon dioxide in the atmosphere. You breathe in a lot more argon than you do carbon dioxide. So not that rare. They've also been called the inert gases, and that's why we say that their common charge is 0. We will almost always find them with a 0 charge, but some of them do react, particularly the heavier ones. So next semester, when we start talking about shapes of molecules, we'll see that sometimes, particularly xenon, will have some bonds to it. So don't think that it never forms bonds. It's just less likely. Going in from there, so going to the left, group 17 is the halogen. So they have a -1 charge. Okay, so left side of the periodic table, metals, positive charge. Right side of the periodic table, non-metals. Now we have the negative charges. So halogens are -1. Now, something to note about chemistry, we kind of get lazy, don't like to have to write things that we don't want to. So sometimes instead of writing out -1, we'll just put a negative sign. Or sometimes we'll, instead of +1, we'll just put a plus sign. So if you see that notation with a dash out there, that just means -1 or +1, as the case may be. Mostly, again, with these names, noble gases and halogens, I will say them in class. So it's helpful to know what I'm talking about. This third name, I'm just putting this here because I put the names of the other groups. Nobody ever really uses that name. So it's pronounced chalcogens, and it is because oxygen and sulfur, the first two elements, are found a lot in the Earth's crust. So there's a lot of oxygen and a lot of sulfides, and they form what we call calxes. And so that's where the name comes from. You don't need to know that. I just like to spew information that's trivial. But that group also tends to have a -2 charge. Now you'll notice that when we get to the bottom of that column, we have polonium, and polonium is a metal. So polonium doesn't really form the -2 charge. So just the non-metals are going to form that -2 charge. Okay. As we move further in, the trend seems to continue, but it's not absolute. So we're not going to worry about nitrogen or carbon or boron, though nitrogen often forms a -3 charge. So if you had to guess, that's where the pattern goes. Aluminum, gallium, indium, thallium, they form a +3 charge very commonly, but they also form a +1 charge. So, you know, there's some variability. Okay, so that's how you can use the periodic table to figure out, is it a metal or a non-metal, and what the common charge is. Okay, so what I want to look at next is a little bit about ions. Most elements are not typically found in their neutral state. So sometimes people will say, oh, a normal atom has the same number of protons as it has electrons. Well, in the case of sodium, that's not true. Sodium is almost never found with equal numbers of protons and electrons. But a neutral atom will have the same number of protons as electrons. Atoms don't gain or lose protons. They're stuck in the middle. They don't go anywhere. But they can gain or lose or share electrons. So all of our chemistry, remember, is going to be about the electrons. So a cation happens when we've lost electrons. So it has a positive charge. This one of your vocab. Now for me, I have cats, I love cats, that's positive, easy to remember. But somebody pointed out to me that cats have paws, so you can remember that they are positive, and that might help you as a mnemonic. Anions, if you think of anti as being against or opposite, anion, these are negative. Okay, and so this happens, anions happen when we have gained electrons, cations happen when we have lost electrons. We will never gain or lose protons, okay? I'm going to try and dispel that myth. All right, so for cations, we tend to just use the element name. So a sodium ion is just a sodium ion. For anions, if it is just an atom and it gains an electron, we tend to change the ending to I. So F is fluorine, and the U and the O are opposite from what you would normally think. F minus fluoride. All right. And even I sometimes, as I'm talking quickly, will say fluoride when I mean fluorine. I'll try not to make that mistake. But that's how we can tell that something is an anion, is with this I. And that's why we don't like to say lanthanides, because they are never negatively charged. So that's why we call them lanthanoids instead. All right, now once we start combining them together with other elements, then they are polyatomic. So if they are oxoanions, we're going to have whatever the element is, and then an oxygen or 2 or 3. So I'm just going to put a little N down here, meaning there's some number of oxygens. Then if it has the higher or highest number of oxygen, then it's going to be 8 instead of I. All right, so I will explain what I mean by that. So if I have NO3 minus, I have 3 oxygens. This one ends in 8, nitrate instead of nitride. Okay, so if I see 8, I should be thinking there's oxygen there. If I have NO2, then the ending is ite. Okay, so that's a lower number of oxygens. So for your quiz, all of the ones that have oxygen end in 8. They're all the highest number of oxygens. Okay. Next week, we'll talk about, well, what happens if you can have 4 and 3 and 2 and 1. For right now, that can be sufficient. Okay. If I want to know the charge of an anion or cation, I can figure that out from the protons and the neutrons. So, the protons have a positive charge, and then we're going to subtract off the electrons because they have a negative charge. So if I have an oxygen that has 10 electrons, an oxide that has 10 electrons, and I want to know the charge, I need to know how many protons are there. All right, so that's the big element that's in the periodic table there. How many protons does it have? So remember what the atomic number tells us? 8. Yeah, the atomic number tells us the protons. So that big 8 there, not only is that it's the 8th element, it's telling us it has 8 protons. So I would say 8 minus 10, that's going to give me -2. And should oxide have a -2 charge based on these rules? Yeah, it's in group 16, the third one over. Okay. What about sodium? Sodium also commonly has 10 electrons. 10 electrons. How many protons does sodium have? 11. Okay. And remember, you guys do have periodic tables on your desk, so if it's too small to see up here, you can always look up there. All right, so 11 minus 10 is 1. So sodium commonly has a +1 charge. Okay. Now, normally, we don't count all the protons and all the electrons and add them up. It's just an exercise that we do here to show you where that charge comes from. Normally, you would be told this is the charge, and then you have to do something. But for the next week, this is a helpful way to figure out how many they have. Now notice that these both have the same number of electrons. Fluoride and magnesium ion also have 10 electrons. We would say they are iso, which means the same, electronic. Okay, because they have the same number of electrons. Okay, gotta do isotopes and 10 minutes. All right. So as I said, iso is a prefix meaning the same. So an isotope is also the same. What the heck is a tope? In this case, it is an element. Okay, so some of you recognized when we were talking about Dalton's rules that when he said every atom of hydrogen has the same mass, that's not exactly true. And isotopes is the reason that most elements are going to form more than one isotope, or they will have more than one possibility of the number of neutrons. In almost all cases, isotopes chemically are identical, which means that a carbon-12 and a carbon-13 and a carbon-14 are going to behave the same way in a sugar, in carbon dioxide, in plastic, wherever it's found. The chemical reactions would all be the same. Doesn't matter what the isotope is. Now, I will say repeatedly throughout the semester that hydrogen is our problem child. So what I just said is not true for hydrogen. We'll not talk about why that is right now. We can get into it later. But isotopes, by and large, really can't be differentiated chemically. They do have some physical differences because there's a slight mass difference. So, for instance, we can separate gases based on how heavy the isotopes are. And then, of course, some of them are radioactive. So in nuclear reactions, they behave differently. In chemistry class, they're chemically identical. But their physical differences and nuclear differences do help us trace what's going on in a chemical reaction. Because if I have one atom that is a different isotope and I can see a physical difference with, for example, with NMR, then I can trace what's going on in the chemical reaction. So have you ever heard of somebody in the hospital having an MRI? So that's magnetic resonance. So NMR is nuclear magnetic resonance. It's basically chemistry's version of an MRI. It's practically the same thing. And so we can use that to trace what's going on with particular isotopes of most often carbon and hydrogen, sometimes other things. Okay, so how do we distinguish things? All right, we use what's called the mass number. Please focus on the word number and not on the word mass because it has almost nothing to do with mass at all. Okay, this is very poorly named. There are going to be people who are going to confuse it with the mass on the periodic table. That is not the mass number. Completely different thing. Okay, the mass number is counting protons and neutrons. We're just going to add those up. And for reasons unbeknownst to me, we are going to use the letter A to represent the mass number. And for reasons also unbeknownst to me, we use the letter Z to be the atomic number. So I don't know why the one that starts with an A doesn't use the A. I didn't make up the rules, but Z means atomic number, A means mass number. Okay, so this is what we would do. We'll take carbon as an example. Almost all atoms, 99% of atoms of carbon have 6 neutrons. So we'll have protons, neutrons, and mass. How many protons does carbon have? 6. So remember, if you're like, how do we know? Where does that come from? You look at the periodic table and find the mass number in there, and that's our, sorry, you look at the periodic table and find the atomic number in there, the number in the corner that has no decimal. So it has 6. So this is 6 plus 6 is 12. So we would call this carbon 12. So about 1% of carbon is carbon 13. How many protons does carbon 13 have? Also 6, because it's still carbon. As long as it's carbon, it's going to be 6. Its mass number is 13, so how many neutrons does it have? It has 7. Okay. And then about 1/100%, a very tiny amount, is carbon 14, which again has 6 protons because it's still carbon, but it has 8 neutrons. So this was originally how things were distinguished because typewriters weren't really good at doing like superscripts and subscripts, making things taller or smaller. But now we like to condense things. And so we use what is called an isotope symbol. Or sometimes you'll hear the term nuclide symbol. That's an older term. And it has 4 parts. All right, so A and Z are here. We said A was mass number, and this is going to be protons plus neutrons, which means it will always be a whole number. It will never have a decimal, okay? Z is our atomic number. What's that equal to? Protons. And then X is just the element symbol. All right, so that's 3 parts. I said there were 4. If it is neutral, we just stop there. But if it has a charge, then we put the charge up here. So that will be the charge, but we leave it blank if it is neutral. All right, so if I were going to do carbon 14, I might write the element C, put a little 6 down here, and put a 14 up here. Now the 6 and the C tell me the same information. They both tell me what atom it is. So sometimes this will get left off. For today, we're just gonna use it, but in the future, you may see things that just have the carbon and the 14. All right, so I have a handout here. This is the assignment that many of you have noticed on Canvas. And I'll let you get started here and finish it over the weekend. After I pass it out, I'm going to point out a few things to you. What you'll notice though is that on the front cover, there's not really anything for you to read. So this comes from a book that really likes to get you oriented towards your learning. So it tells you why it's important to be able to do this and what you need to be able to do. So if you want to see the kinds of things I might ask you, that's success criteria. And then it gives you some definitions if you need them. Does everybody have a copy? All right, so on the inside, the first page is what they call a model. It's just basically, this is how this particular thing works. Here's some examples. And then it has the questions. So I want you to answer the questions. I don't care if you use complete sentences or not. Questions 4, 5, and 6 are really just kind of understanding what you're looking at. 6 is really simple. It's just asking you that you show a charge with a plus or a minus. Okay. For 4 and 5, don't worry about superscript and subscript. The question is not 2 questions. It is saying, what information is provided by the atomic number Z, which is the subscript of the atomic symbol. It is not saying, what information is provided by the atomic number Z, question mark, which is the subscript for the atomic symbol, question mark. That's not 2 questions. It's just telling you that Z is the subscript and A is the superscript. Okay. 7 asks you to distinguish between the mass number, counting up protons and neutrons, and the mass. 12 is really just letting you know that it's really, there's no limit. It's infinite. So I'll just tell you the answer there. And then the back gives you some things to practice. So I'll give you a few minutes to work on that. I will walk around and then I'll stop you a few minutes before the end to go over a couple of things.